Welcome to Mathematics with Tom. I am Tom, and today we are going to look at chapter 4.3 in our text by Gilbert Strang, and this is the section called Least Squares Regression. So let's start there. 4.3, this is Least Squares Regression. Now, if you've ever wondered, this is if you've ever fit a line to a set of data, that line of best fit is the result of least squares regression. And so another title for today might be find the line of best fit. Okay, but of course we're going to do more than that. We're also going to understand the line of best fit, and we're even going to measure it just how far off it is from quite fitting. Well, in order to do that, we need a data set. So here's our data set for today. I'm going to call it, I think we'll call it data set. So here's our data set. Let's start with the values of how about like a 1, 7. I know that's a big one, but we're going to go all the way to 7 today. 1, 7. How about a 2, 1, and how about 3, 1? 3, 1. And you'll see why I picked those values, or at least the third value you'll clearly understand here in a moment. So let me graph these. So if you're graphing these on a piece of paper to kind of keep track, I would encourage you to make your graph a little bit on the larger rather than to err for more than less. And I'm going to extend this down maybe just a little. Okay, and then so now on my horizontal axis, I need to go all the way to 7. So let's do that. 1, 2, 3, 4, 5, 6, 7. Oops, I still went slightly off, but I can fix that. There's 7. And then let's go on our horizontal axis. We have 1. I'm going to space these out. 2 and 3. And because in linear algebra we use x to represent the solution to the matrix equation ax equals b, let's use a different value, like a t, maybe t for our independent axis, and I'm going to use b, and you'll see why, b for my vertical axis. And so let's plot these points. My first point, points are probably best plotted in this pretty yellow. So let's plot with the yellow. So my first point is 1, 7. So let's plot 1, 7. And you don't need dashed lines. Maybe if you have a nice bit of graph paper. So there's the point 1, 7. My next point is 2, 1. So let's plot over 2 up 1. Now, the reason for this is if I was to take and draw a line between these first 2 points, well, that's all you would need. That's the definition of a line, is just connect 2 points. Well, look at what I've purposely done. This next point that we have to graph is 3, 1. Well, as soon as you see this third point, and you're thinking about a straight line, there's no way that you can connect one line to all 3 points unless you have a really fat brush. But we're not going to do that. So the question then is, what is the line that fits closest to all those data? And in other words, we're going to say, what is the line? What is the line that best fits to the data? That's what we're going to find now. So here's what we have. We have this problem of we want a line that's going to fit that. Now let's just think about how we write the equation of a line for a moment. Usually we write it as y equals mx plus b. where y is the dependent variable, m is the slope, x is the independent variable, and b is the y-intercept. And now to make this fit, so this is a little bit of just so visual we can follow the idea. What if I was to just rearrange things? For example, I'm going to put a little arrow here. What if I write this as mx plus b equals y? And let's go another step. I'm going to write the b first plus the mx equals y. Now, we're almost ready to do this. I already said the independent variable is t, and I said the dependent variable is b. And so we need some new letters for this entire problem. So let's use this. Let's call this c plus d times t equals b. Okay, c plus d times t equals b. And now what we can do is we can write the line that best fits. Well, here's what we have. If we have a line that meets this equation, this means that there's some c plus a d times the first t. The first t is a 1, and that should give an output of 7. Well, not only that, but that line should also meet the requirements of c plus d times the input of 2, giving the output of 1. But look, we've got one more data point in our set. So let's see what that meets in this requirement. So this is c plus d. T is 3 and b is 1. And, well, look at what we have. Look at what we have. I'm going to just put this in a little bit better order, maybe just to help see. I'm going to use this orange to just say I'm kind of adding the obvious. I'm going to put a 1 in front of all of these c's. Well, look at this. This is just the vector of c, 1c, 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 plus the vector 1d, 2d, and 3d. So you know what? I see a matrix equation. Let's write this as the equation with the columns. The columns are 1, 1, 1, 1, 2, 3, times c times d equals the vector 7, 1, 1. 7, 1, 1. Now, we know already one problem, and this is not, there's no solution to this problem. Visually, you could see that, and I will just show you. We're just going to use the algebra to check that as well. I'm going to be switching back and forth to develop our pictures here. So let's go to our next screen here, and let me turn this layer off, and let's just see why is it that we know that there's no solution to this problem. Well, if I write my equation 1, 1, 1, 1, 2, 3, I'm going to write just the augmented matrix 7, 1, 1. Let's take a moment and just try to solve this. So in other words, we're going to do a bunch of steps at once. Let's take row 2 minus row 1, and then we'll work on row 3 by subtracting row 1 as well. And let's see, that's going to give us the matrix of 1, 1, 7. So no changes in the first row. The second row becomes 0, 1, 6. Then the third row becomes 0, 3 minus 1, that's 2. 1 minus 7, that's 6. And notice that we have a pivot we've utilized the pivot in the first column. Our next pivot is right here in row 2, column 2. So let's work on row 3. So now I have row 3 minus 2 times row 2. Well, that's going to give me 1. The first row is unchanged, 1, 7. The second row is unchanged, 0, 1, 6. The third row becomes 0. And then 2 minus 2 is 0, and that was as by design. Then we have 6 minus 12 is minus 6. And there it is. There's the problem. This just says very simply that 6 is equal to, or I'm sorry, 0 is equal to minus 6, but we know that this is a false statement. False. This is a false statement. Okay? And when you get a false statement, that's the algebra's way of telling you that something can't work. So in other words, there's no solution. And we already intuitively could see that. So how do we solve that? Well, we solve this by a projection. What we're going to do is we're going to project B onto the column space of A. And we do that by taking the transpose of both sides, and we're going to solve the problem. A transpose A. Let me go back. So remember, this works out as we start with AX equals B, and this has no solution. And what we said then is, well, if we take A transpose to both sides, then we're going to it's not X anymore, because X doesn't exist. We call it X hat. It's our best approximation. This is A transpose B, and we called this the best solution. Or you might even call it the nearest solution. And our author even calls it the best solution, and in reasons we're going to see why I think that was a wise choice of words. So let's apply this. So A transpose is 1, 1, 1, 1, 2, 3 times the matrix of A, 1, 1, 1, 1, 2, 3 times, and then X hat, we could use C hat and D hat maybe to show that's not the original C and D, but we're just going to say it's going to be our C and D because that's what we really wanted. Equals 1, 1, 1, 1, 2, 3. And if you remember, our original B vector, he said, is 7, 1, 1. 7, 1, 1. All right, here we go. So when I multiply these, A transpose A, one way to know if you're correct is you should end with a symmetric matrix. So let's see what happens. That's my first 1, 1, 1 times 1, 1, 1. That's just the sum of 3 1s. And then I have 1, 1, 1 times 1, 2, 3. In other words, 1 plus 2 plus 3 is 6. And again, I have 1, 1, 2, 3 with 1, 1, 1. Again, that's 6. And then the bigger one here is 1, 2, 3 dotted with 1, 2, 3. That's 1 plus 4 plus 9 for 14. Okay. Times the vector C, D equals, and then this is going to be the sum of the B's. Well, that's going to be 7, 8, 9. And then it's going to be 7, 8, 9, and 3 for 12. There we go. Okay, now before I go further, we could solve this. We could start row reducing. But before I do that, I want to just remind you of what this equation means. This is really the system. So this is the system of, and I'm going to come back up here, so let's move over here. This is the system of 3c plus 6d equals 9, and 6c plus 14d equals 12. Okay, this is a key system of equations, and I'm going to give it a name, but not quite yet. Not yet. It's not here. We're not ready for it. The significance has yet to be seen. So I'm going to save that moment. So, what do we want to do here? oh, let's solve this. Let's solve this. I could leave it in the matrix, but I think we're to the point now where I could just very simply say, if I just take row 2 and I subtract 2 times row 1, that's going to give me 2 equations. It's going to give me 3c plus 6d equals 9. And then the second equation is to become 0c, 14 minus 12, that's 2d. And then 12 minus 18 is minus 6. And so we can say d is minus 3. And what else do we have? We have then, so this says that 3c plus 6 times negative 3 equals 9. Well, this just says then that c also is 9. I mean, you take 18, put it to the other side, add it to 9, it's 27 divided by 3, that's 9. And there we have it, we're done. We just found the line of best fit. So let's write what we found, the line of best fit. The line of best fit is C is 9, D is minus 3 times T equals B. Okay, and then, but before I graph that, because I am going to graph that here in a moment, I'm going to graph that. There's something more that I would like to do. So let's do that now. I'm going to come to another screen here. And let's do this. Remember that what we said is that we had that the projection of B onto the plane is equal to A times x hat. Well, in our problem, A is 1, 1, 1, 1, 2, 3 times x hat. That we just found out to be 9 and minus 3. Well, let's see. What is P? That's going to be a 9 and minus 3 for a 6. That's going to be a 9 minus 6 for a 3. And then it's going to be a 9 minus 9 for a 0. So here's what that is. It may not be obvious, but I'd like to show you what this is. Let's return to this. Our best fit is 9 minus 3t equals b. Well, let's see. If I try my t value, so when t, what was our first t value? Our first t value was 1. First t value was 1, and remember that gave me I'm going to call this b prime. And that gave me a b value originally from the data set of 7. So let's find out what b prime is. B prime, and you know what, let's go back in our notes for a moment. Really, our equation should be 9 minus 3t equals b prime equals b equals b prime, because it's going to be more than likely it'll be a value different than the actual b. So let's take a look. So what we have here, so if I put in a t, I get 9 minus 3 times 1. That's going to be 9 minus 3. That's going to be 6, which is the first value in p. As a matter of fact, the projection is the line of best fit evaluated at the original inputs. It's the line of best fit evaluated at the original inputs. And so there we have it. Let's graph P. P is 6, 3, 0. And those are, so really our new points on our line are 1, 6, 2, 3, and 3, 0. All right, let's do it. Let's graph it. So I'm going to go back to my original picture. There's my original picture. So let's see, my first value is a 6. Now I'm going to do this in this pretty blue. And it said we had our first p-value is a 6. So our first p-value is a 6. And so that's going to be right here. My next p-value is a 3. That's going to be right there. And then my next one, when 3, it was 0. 3 is 0. And we also said that b prime, so these are my b primes, or I could call them my p's. I probably should have just called them p. Actually, I think I'm going to go back and make a correction here. Let's do that. Let's fix this. We can do that. That's part of math, is seeing what happens. It's really, this shouldn't be b prime. This should just be not a b prime. This should be a p. Okay, and if we go to this next picture, it should be not a b prime there or there. These should be p's. Okay, so p or b prime, and the reason I say the prime thing is that if you look in a traditional statistics book or algebra book, you'll often see a y prime instead of a y, where y prime denotes the output based on the linear equation, not the original data. So let's continue graphing this. I want to see this. Well, I'm going to connect my line, and if I do, it said I have a y-intercept at 9. That's going to be hard to fit, but notice that if I was to continue, there's 6, 7, 8, 9. If I was to rise 3 and run -1, there's my 9. And if my lines all lined up just how I'd like them to, which probably don't, and look at this. Pretty close. That is my line of best fit, and it would also extend down here as well. Now there's a little bit more we need to see. Let's look at this. Notice that here's my p, my p1. Well, it missed the original data value by, well, I'm just going to call it positive because the original data value is above p1. So notice that I'm going to just call this as my error is 1. My next one says that, oh wow, look at that. My next one here, I missed it by 2, but this time my data value is below the line, the projection line. So let's say that E2 is -2. And finally, notice that my original data now is above. So let's just say this is my third error that I can see, and it's above by 1. Well, let's see how that comes into play. I think you'll be pleasantly surprised. So let's go back to our work here. And notice this. If you recall, the error is equal to b minus p. B minus p. Well, b, we said, is 7, 1, 1. And p, so minus p, well, p is 6, 3, 0. Well, this is going to be 7 minus 6, that's 1. 1 minus 3, that's minus 2. 1 minus 0, that's 1. And look at that. That is the exact same values that we just earlier named. In other words, this is the same as E1, E2, and E3 in our picture. So it's actually showing us the distance above and below our projection line, where the errors from the data. So I want to go on a little bit further, and let's take a look at this. Notice this. Notice this. So this is kind of interesting. So notice this. This is orange stuff if I've ever seen. Notice that E1 plus E2 plus E3. Notice that this is 1 minus 2 plus 1, but that's just 0. Coincidence? Well, let's take a look. Let's see if we can remember. Is that coincidence or is there an explanation for that? So let's do this. Remember, this originally started out with, we had 2 vectors. We had A1, which was the vector of 1, 1, 1, and we had maybe A2, which we said was 1, 2, 3. And then we projected some other vectors, the vector B. and we projected B onto the plane, and let's see, A and B, they described some kind of a plane, a planar structure, maybe like something like this. Well, when we project B onto the column space of A, maybe it's right there, then this is the value of P. That's P, A, X, hat. And not only that, but that vertical line right there, maybe I should have done this in this color, this vertical line here, we said that this is E. And we said that E is perpendicular to the column space of A. Well, what does that mean? That means that E is the inner product of E with any vector in the column space is 0. Well, let's take the one thing we have in every one of our linear regression equations is we have our matrix of A is equal to is 1 1 1 1. Let's do this. 1 1 dot 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 1, and then it's T1 T2 dot 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 Tm. Well, wait a minute. That means that first vector, that in A1, this means that A1 is transpose E has to be 0. But what is A1 transpose? Well, that's always, every single time, it's 1, 1, 1 times E. Well, E is E1, E2 dot 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 EM. Well, look at what this says. That just says that the sum of the E's is 0. E1 plus E2 plus dot 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 plus EM equals 0. So is the sum, so because the columns of the vectors in the column space of A are perpendicular to E, they should be their inner product is 0, and so we always know that the sum of the error components are 0. Now, there's a bit more we need to see here. There's a good bit more. What about this? Let's continue on. We're going to talk about E some more. It's a pretty significant player here because look at this. We started with this problem, AX equals B, and it had no solution. Okay, well, how did we deal with that? Well, what we did is we said that if you take AX and equals B, but you subtracted off the error, well, now you're in the column space of A, and now we have a solution. So we'll say solvable. And that's, well, we can deal with solvable. Well, let's just do some simple algebra. I'm going to rearrange this, and I'm going to say that E is equal to AX minus B. Okay, now, at that point, we haven't done much. And we always know that the sum of the E's is 0. So at this point, how do we measure? How do we quantify the error? Well, think about any time you've measured something, like maybe you measured the house to see how much square footage your house is. In other words, you're finding the length of these spaces. So in other words, let's just find the length. Length is something we can measure. So in other words, if we take the length of both sides, that's the length of E is equal to the length of AX minus B. Now, there's a reason we don't like to deal with the length, and that's because there's a square root. Square roots are just big and difficult to deal with. Well, so what we do is we square both sides, and so what we do, I'm going to leave a little space on the left. We say that the length of E squared is equal to the length of AX minus B squared. And that's the measurement we want. We call that E. And E is really, I'm going to put it over here, this is the error function, and error function is dependent on C and D, the scalars in the line of best fit. And that's it. So we have that our error function, we usually just write it as E, but it is a function of C and D, is equal to the length of AX minus B squared. That's it. Okay. Wow. Let's think about this. Let's see if we can find the error. Find the error for our problem. Let's try this. So the error in our problem, well, remember what the length of this squared is. This is really, the length squared is ax1 minus b1 squared plus. And you'd continue this out to ax, oh, well, depending on how many x's you had, ax, usually in this case it's just 2. How many errors do we have? Oh, we're going to have 3. So you go out to m, I'm sorry. Plus ax m minus b sub m squared. Well, let's just write that. So our first ax1 minus b1 we said was c plus d times 1 minus b1, which was 7 squared, plus our next error was c plus d times the data value t was 2 and the b1 was 1 squared, plus c plus d times 3 minus 1 squared. And there, now we can find the error. We can measure the error for a problem. But before we do that, let's do this. Minimize. Let's do some calculus. This is very calculus. Minimize e. Okay, we can do that. So when you talk about calculus, if you see the words maximum or minimum or maximize or minimize, it means what you're going to do is take a derivative and set it to 0 and solve. Well, I have two variables. So what we're going to have to do is we're going to have to take a derivative. So when you have if I only variable in here was c, for example, I'd write the derivative of e with respect to c. But when your function has more than one variable in it, we call those partial derivatives, and we say, so we use this kind of, it's like a bent over d, or kind of squished. So it's like the partial derivative of e with respect to c. So I'm just writing this for those of you that have not seen a partial derivative. It's okay, you'll be able to follow this. And so I need to take the derivative with respect to c, and I'm also going to find the partial derivative of e with respect to d. And here's how we do this. I think we have just enough room up here. So what we do is we're going to take the partial derivative of e with respect to c. So what that means is that only c is a variable. D is now treated as a constant. D is now treated as a constant. So here we go. I'm going to write this as the equation of, this is 2 times what's inside. Well, that's c plus d minus 7. Then 2 minus 1, this becomes a 1, times the derivative of the inside. Well, the derivative of c is 1, the derivative of d is 0, and the derivative of negative 7 is 0, so this is going to be times 1 plus 2 times, then I have c plus 2d minus 1 to the first times the derivative of the inside. Well, that's just going to be a 1 plus 2 times c plus 3d minus 1 to the first times 1, and all of that is 0. And now let's just do some cleanup. First off, we can divide out by 2. So let's just do that and make our life nice and easy right off the bat. And let's gather our c's. Here's a c. There's another c. That's 2 of them. There's another c. That's 3 of them. So there's 3c. Let's see what else I have. I have a d. 2 more. That's 3 plus 3 more. I have plus 6 d's. And then I have 7 minus 7, minus 8, minus 9 equals 0. I'm just going to write this as equals 9. Then let's do this. Let's write the partial derivative of e with respect to d. Well, it's going to be a similar process, so here we go. So remember, all of this is based off this equation down here with the kind of greenish color underlined. We're taking the derivative of that, but this time the variable is d, so c is treated as a constant. So it works out, it starts much similar. So we take 2 times, then we're going to have a c plus d minus 7 times the derivative of, with respect to d of the inside, well, that's going to be 1, plus 2 times, I'm going to have a c plus 2d minus 1 to the first times the derivative of the inside, well, that's going to be 2, plus 2 times, then the inside, well, that's going to be c plus 3d minus 1 to the first times the derivative of the inside, it's going to be a 3, and that equals 0. Okay, let's do the same thing. We can divide out by 2, make our lives much easier. So I have c plus another c, that's 2, plus 1 more, I have 3c. And then, let's see, here's a d, 2 more d's, that's 3d, plus 3 more. Oh, wait, that's not it at all. Goodness, here's a d. Here's a 2d, but it's going to be times 2, so that's really going to be, oh, that's not even 3c. I did it all wrong. Okay, here we go. c plus, I have 2 times c. That's going to be, oh yeah, 3c plus 3 times, that's 6c. So I have 6c. All right, d's. So I have d. Now this is going to be a 4d, so that's going to be 5d. 5d plus 9d, that's 14d. Okay? I have minus 7, minus 2, that's minus 9. Minus 9 minus 3 is minus 12, but I'm going to just put it on the other side as equals 12. Well, wait a minute. Look at this. Look at this. Look at what I have. Right there and right there. Those are the exact same equations that we found right there. There is no coincidence. Oops, sorry about that. My layers kind of messed up. So this is the same set of equations. And what they're called is these are called the normal equations. Normal equations. And what happens is, notice, and let's go back to where we were working so I have more space, is this is our key point, is the normal equations come 2 ways. Come from A transpose A, x hat equals A transpose B, and from the minimizing the error function, e of c and d. Okay? 2 different routes to the same result. The most common one that I think most people are most familiar with is the route from calculus. I think the route from linear algebra is so much cleaner and elegant. All right. I think we found all the pieces. We've found our error. We've understood our error. We've found the relationship between the error and the calculus and where that comes from. So there's one more thing I would like to do. And in order for that, I think we need a fresh start. So let's come to one last page. Here we go. And this is what I think you need to see, is normally the matrix A, let's do this. Write the general solution, the general equation to find the line of best fit. Okay, so what this is for each set of data, you will have an equation that should match. And so for every single equation, you're going to have some C plus D times T sub I equals some component B sub I. Well, this gave us the system of equations of, well, all the C's are going to be 1. And we're going to have M, line of best fit. I should do this. 4 T ordered pairs. Okay, so 1s. And then we're going to have T1, T2, all the way down to Tm times CD. And this has to equal B1, B2, dot, 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 B sub M. Okay, this has no solution. How do we solve it? We solve it by solve as A transpose AX hat equals A transpose B. And so what I want to do now is find, let's do this, find A transpose A and A transpose B. All right, let's do that. So A transpose A. Remember, this is going to be, I'm going to bring it back up here. This is going to be 1, 1, all the way up. We're going to have M of those times T1, T2, Tm. We're going to multiply that by the matrix of A. Well, that's a 1, a 1. All the way down, we're going to have M rows, and then we're going to have T1. And our next data set has a T2, and then our last data set has a T sub M. There's M different data sets. Well, let's multiply this together. If I take the first row times the first column, this is going to be 1 plus 1 plus 1 plus 1. But there's M of those 1s being added up. So the sum of those 1s is just a 1. The next row says row 1 times column 2. Well, that says T1 plus T2 plus dot, 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 all the way up to Tm. In other words, that's the sum of the Tm's. And now I could put as I go, as M goes from, I could do it this way. Ti, as I goes from 1 to M. I'm going to leave off that extra notation that's going to be implied for all summations in this. And again, if I have another row 2 times column 1 is going to be the same thing. And that makes sense because we already said that this is symmetrical. So it's the sum of the Ti's. The next one is going to give me T1 times T1. That's T1 squared plus T2 times T2. Well, that's just the sum of the Ti's squared. Now, this is A transpose A. Let's try again. A transpose B. A transpose B. Well, this is again, let's write it out. 1, dot, 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 1, T1, T2, dot, 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 Tm. And then we're going to have B1, B2, dot, 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 B sub M. Well, that's going to be 1 times bm plus 1 times b2. I think I said bm. 1 times b1 plus 1 times b2. Well, what is that? That's the sum of the b's, of the b sub i's. And then the next one is going to give me the sum of t1 times b1 plus t2 times b2. In other words, it's ti times bi. All right, we have just enough room to put this all together. I'm going to write this now as the normal equations. So the normal equations say that 1 times the sum, I'll write it this way, sum of the ti, and then the sum of the ti, sum of the ti's squared, times cd has to equal the sum of the b sub i's and the sum of the t sub I b sub i's. Well, wait a minute. Let's just write this first equation. This first equation says that 1 time, oops, not 1, that's not a 1 over there. Hopefully you knew better. That was a c or an m. Oh, this should have been an m. Way up here, that should have been an m. Sorry about that. So now I have m times c plus d times the sum of the ti's. This has to equal the sum of the b sub i's. Divide everything by m. So this is that c plus d times, I'm going to write it this way, the sum of the t sub i's divided by m is equal to the sum of the b sub i's divided by m. Well, notice this. What is the sum of the ti's divided by m? Or the sum of the bi's divided by m? Well, think about that. What does that mean? So that means you take the first t value plus the second t value plus the third one. Say there's 3. Add them up and then divide by the number of t's. There is 3. Well, that's the average. Sure. I'm going to write this as c plus d times t hat. T hat means the average of the t's. Equals, well, this is the average of the b's, so we'll call it b hat. Or you could call it b bar if you wanted. But there it is. In other words, this says that the average of the ti is ti on the line of best fit equals the average of the original b's, bi. That's right, it's built right into the equation itself. That's a lot to absorb. I hope you enjoyed and I hope this helps. Thanks for watching.